Normal curves and sampling distributions. In this video, we will discuss the normal distribution, including its percentiles within the standard normal distribution, as well as the non-standard normal distribution and the exponential distribution, along with other continuous distributions. Unlike the binomial and Poisson distributions, the Gaussian distribution is continuous and is widely used in science. Often referred to as the bell-shaped curve or normal distribution, the Gaussian distribution is known for its characteristic shape and its prevalence in statistical analyses. Normal distribution is a fundamental probability distribution in statistics, characterized as a continuous probability distribution for a random variable x. Its graphical representation is known as the normal curve. If x is a continuous random variable with a normal distribution characterized by a mean mu and standard deviation sigma, the normal curve can be graphed using its equation. The properties of normal distributions include that the mean, median, and mode are all equal. The curve is bell-shaped and symmetric about the mean, the total area under the curve equals 1, and the curve approaches but never touches the x-axis as it extends further from the mean. In a normal distribution, the mean can be any value, and the standard deviation, which must be positive, describes the spread of the data. Standard normal distribution is a normal distribution characterized by a mean of 0 and a standard deviation of 1. In the standard normal distribution, the cumulative area is approximately 0 for z-scores near z equals negative 3.49 and approaches 1 for z-scores near z equals 3.49, with the cumulative area increasing as the z-scores increase. For a z-score of 0, the cumulative area is exactly 0.5000. Standard normal table, also known as the z-table, provides the cumulative probabilities for the standard normal distribution. It shows the area under the curve to the left of a given z-score, which represents the probability of a value being less than or equal to that z-score. The table is used to find the probability associated with specific z-scores in hypothesis testing and confidence intervals, helping to determine how likely a value is to fall within a certain range in a standard normal distribution. To find the cumulative area corresponding to a z-score of 2.71 using the standard normal table, locate 2.7 in the left-hand column and then move across the row to the column under 0.01. The area to the left of z equals 2.71 is 0.9966. To find the area under the standard normal curve to the left of a given z-score, refer to the standard normal table to determine the corresponding area. To find the area under the standard normal curve to the right of a given z value, first use the standard normal table to determine the area corresponding to that z value. Then subtract this area from 1 to obtain the area to the right of z. To find the area under the standard normal curve to the left of z equals negative 2.33, refer to the standard normal table, which shows that this area is 0.0099. To find the area under the standard normal curve to the right of z equals 0.94, consult the standard normal table, which indicates that the area is 0.1736. If p does not appear, the closest value to p is often used, although linear interpolation provides a more accurate result. Percentiles of the standard normal distribution correspond to specific z-scores, indicating the value below which a certain percentage of data falls. To find the 100p th percentile, locate the value closest to p in the standard normal table and identify the corresponding z-score from the table's rows and columns. For example, the 67th percentile corresponds to z equals 0.44. 99th percentile of the standard normal distribution is the value on the horizontal axis for which the area under the z-curve to the left is 0.9900. In this case, 0.9901 is found at the intersection of the row labeled 2.3 and the column labeled 0.03, so the 99th percentile is approximately z equals 2.33. By symmetry, the first percentile is positioned as far below 0 as the 99th percentile is positioned above 0, making it equal to negative 2.33, with 1% of the data lying below the first percentile and also above the 99th percentile. To determine the 95th percentile of the standard normal distribution, we search for 0.9500 in the table. Since 0.9500 is not directly listed, we find the closest values, 0.9495 and 0.9505, which correspond to z-scores of 1.64 and 1.65, respectively. Given that 0.9500 is midway between these two probabilities, we use 1.645 as the 95th percentile and negative 1.645 as the 5th percentile. Non-standard normal distributions are those that do not have a mean of 0 or a standard deviation of 1, unlike the standard normal distribution. To work with these non-standard distributions, data must be transformed into the standard normal form using the z-score formula given, where x is the value from the non-standard distribution, mu is the mean, and sigma is the standard deviation. To convert a normal distribution to a standard normal distribution, you use the z-score formula. This process involves transforming the data from the normal distribution, which has any mean, mu, and standard deviation, sigma, into a standard normal distribution, which has a mean of 0 and a standard deviation of 1. Given that the average test score on a statistics test is 78 with a standard deviation of 8, and assuming the test scores are normally distributed, we want to find the probability that a student scores less than 90. To determine this probability, we first need to calculate the z-score for a test score of 90 using the given formula, where x is the test score, mu is the mean, and sigma is the standard deviation. Substituting the values, we get z equals 1.5. Next, we look up the z-score of 1.5 in the standard normal distribution table. The probability associated with a z-score of 1.5 is approximately 0.9332. Therefore, the probability that a student receives a test score less than 90 is 0.9332. Average score on a statistics test was 78, with a standard deviation of 8. Assuming the test scores are normally distributed, we want to find the probability that a student receives a score greater than 85. To determine this, we first convert the test score to a z-score using the given formula. For a score of 85, this becomes z equals 0.875. Next, we look up the z-score of 0.875 in the standard normal distribution table. The probability of scoring less than 85 is approximately 0.8106. To find the probability of scoring greater than 85, we subtract this value from 1:1 minus 0.8106 equals 0.1894. Therefore, the probability that a student scores greater than 85 is 0.1894. Exponential distributions model the time between events in a Poisson process, where events occur continuously and independently at a constant average rate. This distribution is particularly useful for calculating the reliability of electronic devices such as laptops, batteries, processors, and mobile phones, helping engineers and manufacturers estimate the expected time until a product is likely to fail. An exponential distribution is a continuous probability distribution often used to model the time between events in a Poisson process. It is characterized by its rate parameter, lambda, which is the average number of events occurring in a unit time interval. In an example involving exponential distributions, consider a model where the stress range in certain bridge connections follows an exponential distribution with a mean value of 6 megapascals. Given that the mean value x equals 1 divide lambda equals 6, it follows that lambda equals 0.1667. To determine the probability that the stress range is at most 10 MPa, and the probability that it falls between 5 and 10 megapascals, we need to apply the exponential distribution formula. The probability that the stress range is at most 10 megapascals is 0.811, as calculated using the exponential distributions formula, as detailed here. The probability that stress range is between 5 and 10 megapascals is 0.246, as calculated using the exponential distributions formula as explained here. Weibull distribution is a continuous probability distribution frequently used in reliability engineering, life data analysis, and survival analysis, particularly for modeling the time until failure of a product, system, or component. Its flexibility allows it to model various types of failure rates, depending on its shape parameter. Weibull distribution is widely used in reliability analysis for estimating the lifespan of products, in survival analysis for modeling lifetimes in medical research, and in weather forecasting to predict extreme events such as wind speeds. Weibull distribution allows for variation in both the shape parameter, alpha, and the scale parameter, beta, resulting in a diverse array of density curves, as illustrated in the accompanying figure. A log-normal distribution is a probability distribution of a random variable whose logarithm is normally distributed. Thus, if xi is a random variable with a log-normal distribution, then log x follows a normal distribution. Log-normal distribution finds diverse applications across various fields. In finance, it is used to model stock prices and financial assets, where prices are inherently non-negative and returns tend to be multiplicative. In environmental studies, it helps model phenomena such as the distribution of particle sizes and species populations. In reliability engineering, the distribution is applied to model the time to failure of systems and components, particularly when failure rates follow a multiplicative pattern. Figure illustrates the graphs of the log-normal probability density function, PDF. Unlike the symmetric normal curve, a log-normal curve exhibits a positive skew. Beta distribution is a continuous probability distribution defined on the interval 0, 1, and is frequently utilized in Bayesian statistics, machine learning, and decision theory to model the distribution of probabilities. Figure illustrates several standard beta probability density functions, PDFs, showcasing various standard beta density curves. Thank you for watching.